Gets to it. Okay, well, hello everyone. Welcome back to Introduction to 3D Printing. We are on to week 2. So thanks, folks, for sending me assignments and stuff. That was great. So that the job there was to let's have a look at a couple of prints and see how they came out. And I think it'll be interesting for some of you to see sort of like how does a concept in your head actually work out in real life when you actually have a look at the prints? So I've got assignments from both classes, and I'm just going to sort of just like wave them in front of the camera in a second. But before we go on, let's just have a quick look at what we're going to cover today. So this week we're going to cover reviewing the assignment. We're going to have a look at what does it mean to design and for 3D printing, basically. So if you want to design inside a computer, or even design for sort of like copying stuff you found in real life, what does that take? What does that look and feel like? We're going to have a little bit of a look at the slicer, which is in the the traditional middle step for 3D printing. So it's a very necessary technical step in terms of preparing your print ready for printing by the actual physical printer itself. We're going to have a look at supports and rafts, which are very important in terms of maintaining print quality, and just having a look at how does that affect the quality of the print. And I'm going to show you some examples with that. And then we're going to go into a second round of basics for Tinkercad. Awesome. All right, so let's have a look at the assignment and sort of some of your submissions. So I'm going to bring this, get the overhead camera up. Okay, fantastic. So these were really interesting. I received a really interesting set of submissions, and I think Sebastian, you had a little bit of a handle in terms of like what was going on and what could potentially happen. But I was just going to start with this piece, this submission here, because it was pretty interesting. So this was a piece here that has a heart-shaped object and a very complex sort of key mechanism which goes into a keyhole. It looks extremely cool. But, we can see that like there are already going to be some problems with this in that it is the exact same size. And what that comes down to is, you can see like, this top part here, it slots in pretty easily, but these teeth, there's no traction, right? There's it fits in so exactly, I really cannot get that sliding in. And it was a similar story for sort of like other sort of like complex object submissions, like this one here. And it was a little bit of a cheat in terms of the assignment that I sent you. I think, getting, in the first week, getting two objects to sort of fit together is going to be very, very difficult, partially because you're missing some information that you needed, right? And the information that you really needed to know to sort of like make any of these, a key and a keyhole submission fit together is really understanding some of the tolerances of my individual printer, right? And this is something that you really need to sort of, once you actually get a printer, spend a little time figuring out, is really sort of like, how does your print warp and change when you get it into the printer, and what are the actual sizes of the objects that are going to get printed out? And the tolerances that we're talking here are like, 0.1, 0.2 millimeters, right? So it's really small, but it makes a significant difference when you're trying to get two objects that are going to try to slot together. And the reason that you get that kind of tolerance is that the nozzle itself on the printer is quite small, right? So we're talking about on the order of like 0.4 millimeters, but it's not 0, right? So it's not an exact line. It's not an exactly, it's not a super tiny amount of plastic that's being put down. So you have two things that are going on, right? So one of them is that when the nozzle squirts out the plastic, it does blob up a little bit on the way out, right? So it sort of expands a little bit, but it also cools as well. And the contraction that you get is really based on the, locally what's going on in that part of the object that you're printing out, right? So if it's a really sort of like complex feathery shape, that's going to expand and contract slightly differently to when you're printing out, say, like, a large block of material like you'd get around the edge of like one of these pieces that are here. So what does that, how do you actually account for that? And one of the things that I think like a good sort of like calibration step that you can do once you have a printer looks a little bit like this, right? So I'm going to switch to Tinkercad here. So the way that you'd account for it would be, tell you what, let's how about we create like a little like object here that we're gonna use here for a test. So I'm just gonna create a little F-shaped thing, and that's gonna be very, very similar to sort of like the assignment. So it's gonna be like a key-shaped object. So I'm just gonna take this and stretch this out over here. Maybe make this a bit thinner. And then I'm going to make another copy of that. And there we go. Okay, so that's going to be our sort of like typical key shape that we're going to use. I'm going to do this and, I'm going to take those and I'm going to combine them together. And then let's create another box that we're going to cut this out of, like so. And copy that. Okay, so I'm going to move that aside, and that's going to be the key that we're going to use. I'm going to change this to a hole shape. So we've got our key and our keyhole that we want to work with. Now with Tinkercad specifically, I think one way of correcting this is basically adjusting these inside surfaces that are here. And that's harder than actually adjusting the object that you want to slot into it. And this is really important to note. Shrinking the whole object uniformly is not going to do it, because if we do that, you run into problems like this, right? So I've shrunk this whole object uniformly, but the space between the forks has shrunk as well, right? So you can see that there's appropriate space all around the edge of the object, but the space between the forks has shrunk as well. So that's not going to be much good to us. So so instead what we're going to do is, sorry, I just need to go back a couple of steps. Instead of shrinking it that way, what we're going to do is I'm just going to temporarily hide that object. And what I'm going to do this is I'm going to ungroup it. The thing that you want to do is you want to take all of your outside surfaces and you want to shrink those, right? So, I'm going to move this in a little bit, going to move this in a little bit. I'm not being very precise here. When you are doing this for real for yourself, what you want to be able to do, you do want to be more precise, right? Because you want to base this on the tolerance of your printer, and I'll get to that in just a second, how to figure that out. But I'm just going to make this little adjustment here, and then I'm going to do the same thing for here, just adjust the top and the bottom, and then this last bit here. So I've adjusted all the external edges here, so I'm not being super precise here. But then if I group this all together and I unhide my object here, you see that if I then take this key and I try to move it into this shape here, you can see that it's got a nice sort of like area around it, so it's going to fit in. The idea is that when you do this shrinking, you'll do it based on the amount of tolerance that you have. And one of the simplest things that you could do for sort of figuring out what the tolerance of your printer is printing out a like a nice simple one is that you can, I'm just going to delete these, so I've got another clean workspace. What you can do is that you can take a cylinder and then you can basically make a hole in a box with it. So I'm just going to make this bigger here. I'm going to take this here. So that's going to be your test cylinder, right? So you want to keep a copy of that. And then, you want to start with a version of this box that has that same size hole in it, and you basically see whether it fits. Then what you do is that you make the cylinder just a tiny bit wider. So you want to increase it by however much, and then do the same thing. It's like be precise about it. Look at the numbers as they change, and then print out a slightly larger version, and then so on, right? So you can do that by printing out several of these. Another thing that you can do instead is that you can actually make a stair-step pattern. So what you do is that you make the bottom make the bottom hole basically the same size as that, but then you take a slightly larger cylinder, lift it up a little bit, so you create sort of like a series of gradually larger sort of concentric circles. And then what you do is that you fit your test cylinder inside that to see how far does it go within those sets of concentric circles. And that gives you an idea of, for example, like how much has the, you basically halve the difference between the two, and then you get an idea of basically how much does your material tend to expand when you have that kind of joint. And what you'll find is that you'll find that your circular surfaces are going to have a slightly different expansion than you get than you get with, say, like flat edges like this. But it's it's one of those things that you probably want to calibrate a little bit with your printer, and you'll find that it's also going to be slightly different for each type of printing material that you use as well, right? So if you're using PLA, that'll probably give you one set of tolerances versus, say, like a harder type of plastic like ABS. As the plastic cools, it's going to expand and shrink a little bit differently. But once you have that, that'll give you an idea of, for example, like how much, what are your tolerances when it comes to basically like slotting objects together, and when it comes to sort of like adjusting them that way. So does that sort of make sense? All cool? Awesome. All right, cool. All right, so back to the slides just for a bit. Designing for art. This is one of my favorite topics. I really like. I really like the idea of making some art and then putting it on the 3D printer and holding something in my hand. But getting models into your 3D printing workflow can get a little exciting sometimes. So, and I wanted to talk about sort of like some options that you'd have. One of them that I quite like is photogrammetry-based workflows, where what you do is that you take lots and lots and lots of photos of the object that you'd like to be able to get into the computer, ideally with sort of like reasonably flat lighting, and then you load them into an application like Reality Capture or Meshroom from Alice Vision. That's an open source one that's quite good. And what you can do is that you can use those collections of images to build a 3D reconstruction of the object that you had. They tend to require a little bit of cleanup, but usually it's not too bad. But then what you've got is that you've got a nice sort of like textured object which you can take and then run into other applications as well for like adjusting and tweaking, and then you can pretty much just sort of like drive a 3D print straight from that. That's fun, but it is sort of fairly labor intensive. Another thing that's fun to do is just classic kit bashing. So what you do is that you take your objects, and then you basically take objects that you've already found, right? So typically you'd look on somewhere like Thingiverse, which has a large collection of already made 3D objects. And then what you want to be able to do is that you cut and you slice them and you just rearrange them to make a completely new object. And that's actually something we're going to cover in the exercise today a little bit later on. But that's a good way to get sort of like a very quick bit of novel satisfaction out of 3D printing. I quite enjoy it. It's one of my favorite things. There are more traditional approaches, of course, right? So, doing sculpting straight in the computer. The big sort of like 500-pound gorilla in this space is ZBrush. ZBrush is very popular with artists, and it seems to be one of the dominant sculpting applications. It's very sort of like tablet friendly if you have one. And so as in like working with a Wacom tablet or something like that. And it's a very common application that is sort of like not exactly a drop-in replacement for sculpting with clay, but it definitely has a little bit of that feel. And you can use that to very quickly sort of like iterate on creating an object and adding detail and adding lots of bits and pieces that you think could be sort of like to make it interesting for 3D printing. There are open source options available as well. Surprisingly, Blender 2.8 Sculpt is very, very good. It's very well reviewed. Blender 2.8 just in general has been a revelation as far as Blender goes. It's been a significant change in the user interface as far as like free 3D applications go, and people are actually using Blender now for doing 3D modeling for 3D printing as well, which is fairly impressive. So if you're interested in sort of open source tools for doing this, it's one that I would recommend as sort of like an end-to-end workflow for 3D printing. It's fairly impressive. And yes, it's got a very nice sculpt mode if that's how you would like to generate your objects for 3D printing. On the virtual reality front, people are doing a lot of sculpting in VR now as well. I should really correct that. It's Adobe Medium, not since they came to join us last year. So Adobe it is part of the Adobe suite now, and Medium is a sculpting tool for VR that has based on sort of like your I guess your clay/sculpey type environment, where what you're doing is that you're working with a hunk of material in front of you, but then you use the controllers that you have in VR to sort of have a go at the material and sculpt something. I've seen this at a number of conferences where people have used these to generate some quite detailed sculptures, which then get 3D printed. This is a very popular technique, and there's something nice and tactile about doing this. It isn't quite like working with Sculpey or clay, but it does feel very good and it feels very satisfying. People also have other kinds of art-based workflows that are like or involve 3D printing. One of them that I wanted to call out because it's just so weird and so cool was using tilt brush. So tilt brush, the concept there is that, again, it's in VR, but you draw kind of ribbons in space to make your objects. And this artist, Jonathan Yeo, worked with the tilt brush group over at Google, and they figured out a way of getting his brush strokes rendered out as geometry, which could then, I believe their initial prototyping was using 3D printing, and then they ended up scaling that up larger and larger, making casts. They ended up making a bronze cast of a tilt brush artwork of someone's head, and they're able to get that made. And I believe this is in a museum in the UK, but I forget exactly which one, a museum or a gallery, but it's very, very cool, very impressive, extremely heavy. But it's another really cool example of where folks have used 3D printing, they've used 3D sculpting to render something sort of completely in a computer, but then, you know, you're able to get next to it in real life, which is really, really cool. So yeah, there, like I said, there's tons of options, and you know, there's also all the other sort of like traditional 3D approaches. So you can, you know, you can put stuff together in Maya, or like I mentioned, Blender, or whatever, like, you know, 3D content creation application that you have. And you know, if you're expressive in those tools, then go ahead and use them for sort of generating your 3D objects. The important part is to sort of have it in 3D. And the nice thing is that you don't have to worry about texturing or lighting your object, because that's what you're going to do in real life once you've actually printed it out, right? So you don't need to worry about color or anything. So you can stop at that step and just worry about the shape, which is also a nice sort of thing that you don't have to do. All right. I wanted to talk a little bit about orientation and accuracy when it comes to 3D printing. And it's worth noting that certain orientations are going to give you better quality prints. So I'm going to switch back to the overhead camera view just for a moment. So I'm just going to pick up a couple of these pieces. I seem to... Okay, here we go. Got it. Okay, so with these... what I've done here is that I've printed out the same cylinder but twice, and I've got like a little test object that I'm going to use here to measure the accuracy of the fit. So when I printed these out, this is what my intended goal was. So let me just bring this up. Just give me a moment. I've just got to load up my object in Tinkercad. Okay, so let me just switch you briefly to this. So when I printed my objects, what I did was that I printed it so one of the cylinders was coming straight up out of the plate, and the other one was laid on its side. And I wanted to show you what that does to the print when you're printing something straight up versus on its side. And if we go back to the overhead camera here, this is the one that I printed straight up. And you can see that when it comes straight up out of the plate, the dimensional accuracy there is quite nice. It's quite uniform. It's quite smooth. There's a little bit of striation in the middle because 3D prints do string a little bit, but they're fairly easy to sort of like trim off with a hobby knife. That's what I did. And you end up with a fairly sort of clean print. Compare that with when I printed the object on its side, right? So I took the cylinder and I printed it on its side. You can see it's got fairly rough edges, but note the warping on this, right? So you can see this is the bottom part here is where the flat part sat on the plate, and it's flattened out. It really has sort of flattened out quite significantly. There were supports in the middle to prevent this sort of completely collapsing while it printed, but even then you can see it really doesn't have a nice degree of roundness. And when I take my sort of test cylinder and I try inserting it into the one that's sort of dimensionally accurate, there really aren't many problems. It's a little stiff and it's a little tight because I intended it to be, but it does sort of fit fairly nicely. Whereas compared with this one here, I can't even get it started. Like there's no way that I can even get it to sort of click in even vaguely. And what this really comes down to is that prints that are coming out off the print bed, right? So when you are imagine for a moment, right, that this surface here is the print bed. When we are printing stuff off the print bed, stuff that is in sort of like X and Y, so stuff that is in the plane of the print bed is going to be pretty accurate because the print head itself can move in that direction, it can move in this direction, it can be placed extremely accurately. And when it's printing, it's a continuous thing, right? So it's like a plotter that's plotting, right? So you can imagine there's like a pen that's going, and it's just sort of continuously going around, and the motion's very smooth. But then to go to the next layer, the bed has to move, and then everything will sort of like pop up a little bit, and then it will start doing the next layer. And the way it does the next layer is that it's got to melt that layer that it's added on top of the previous layer that's there. And you can imagine that isn't nearly as accurate. So what will happen is that as you go up out of the plate, things get less and less and less accurate. And the greater the angle that's there, the less accurate that it's going to be. So to give you an idea of what that looks like, I'm just going to bring up another test object. Bear with me just a second, which is going to be, let me just wait for this to come up. It's going to be these 3 weird looking triangle shapes that I printed out. And these are sort of fairly illustrative, right? So what I did was that I printed these in this orientation. So when they got printed, they had one flat side down on the bottom, and then they went up out of the plate. And the thing to note is what happens at the bottom of these triangles. So I'm just going to arrange them for you in front of the camera, like so. And let me just bring up the camera. Okay, so when we've got these, note how much rougher the pieces get as we go along, right? So when we've got this piece here, the angle is actually nearly vertical, but it's not too bad. You can see that the bottom surface here is pretty rough, and the top surface is pretty nice. But even then, you can start seeing that there's some errors around the edges when it sort of like steps from one level to the next. As this angle increases, so as it sort of gets more and more, as it starts leaning out more and more and more towards the plate, we start getting rougher, right? So you can see this edge here is pretty rough. Again, the top nice and smooth, but it's this bottom edge here that's problematic because it's starting to go further and further out. And then when it starts going a long way out, it gets really rough, right? So you can see that you've got these edge problems here, and you can even see that you start getting thermal problems, right? Because you have this little thin piece here, and this nose on the end that's sort of hanging out in space starts warping up all on its own. And what you're seeing there is that when you're arranging your things to print, especially if you're printing something artistic, the undersides of the objects aren't going to look as nice. So when you are arranging stuff on your plate, once you're deciding which way up that I want to be able to print something, note that the bottom of the objects aren't going to look as good. And that's going to remain the case even if you have supports, right? So I'm going to get into supports in a little bit more detail in a second, but when we're talking about supports, we're talking about, adding support material when it prints, right? So what we have is that we'll have a raft on the bottom so that this sticks nicely to the build plate. And then we've actually got these weird sort of like zigzag supports which get printed underneath the object, and then you just basically snap. You take your printed object and you basically snap it off the top there. It's quite nice. But even then, you're still going to get a certain amount of roughness on the bottom of the object. And, these are sort of like abstract geometric shapes, but they, even then, there can be sort of like problems with how you work with that. So let me get to the next slide. If I get to the slicer, before we go, there's one more thing that I wanted to show you, which is this object here. So I printed out this. Sort of like weird object here, and I printed this out without any supports. And what I've done is that I've got these 5 little fingers that go out 1 centimeters, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters, and there are no supports at all on the bottom. So you've got these fingers that are sort of like pointing out onto the space. And how did I thought this was going to go extremely badly, but the printer still did surprisingly well. But it does illustrate a point, right? So from the top, it sort of like looks kind of like how you'd expect, but underneath, it's tragic, right? And it's a little bit more illustrative. If you look from the side, you can see what's happened. So what's happened is that without having any sort of like gradual way of getting like gradually ramping up to that level where you got these fingers sticking out, you can see that you get in 3D printing, it's just referred to as spaghetti, right? So you get this spaghetti at the bottom where the print hasn't had anything to hold on to, so it's trying to draw these really, really long lines out into the middle of space but they don't have any support on them, right? So you print out this long line, there's nothing underneath it, so it sort of turns into this wiggly spaghetti. But despite having to go out 5 centimeters, it somehow did actually manage to recover a little bit and at least make an attempt at printing these fingers. Then these came out, the top surface of this came out way better than I thought it would. But you can see, again, there are sort of like thermal problems with this. Without a proper support on the bottom, these fingers sort of start bending up towards the edges. And I think if you look from the other side, you can see how it gets gradually worse and worse the further out that you go. So that's why it's really important to have rafts, and it's really important to have support material. So that's actually a good point to sort of like jump off and have a look at slicing and how can you add support material to the bottom of a print just to make sure that your material is so that the objects that you're printing, the models, are properly supported and not going to do weird things during the print. So when we talk about slicers, again, like I said, when I mentioned before, the slicer is the middle step. It's the middle step where what you do is that you create your object, then you slice it, and then you send it to the printer for actual physical printing. Two popular slicers, I mean, there are a lot, but the two popular slicers and the ones that I'd recommend that you look at are Ultimaker Cura, completely free, and Slicer as well, with a weird 3 for the E. Both of them are pretty good tools for taking an object and slicing it into bits, making it ready for printing. And the two primary parameters that you really have to worry about are infill and wall thickness. So let's have a look at what that means in terms of printing a model. So I'm going to bring up Cura here, and then we can take a look. So Cura is a pretty simple interface. You can just basically drag and drop your models into it. So I am going to find something on my desktop. Bear with me just a moment. Let's see what I can find. Okay, here we go. Okay. So because he's been all over the telly, he's kind of fun to work with. I'm going to bring in Baby Yoda. So my apologies to Baby Yoda in advance. But he makes an interesting test subject because he's got lots of very interesting geometry. So what I'm going to do now is I'm going to scale him a little bit because he's way too big for the build plate. So I'm going to make him 10% of the size. And let's take a look at him a little bit closer. So what matters here are wall thickness and infill density. So what I'm going to do, just to make things simple, is that I'm going to change the infill density to 0, and I'm going to change my wall thickness to 0.1 millimeters, really quite thin. And then I'm going to change this to the layers view so that we can actually have a look at what's happened to Baby Yoda. So in fact, I'm going to bear with me just a moment. I'm just going to turn off support. I'm also going to turn off build plate adhesion just to make it simpler and faster. Okay, so let's see. So he's being sliced. Okay, so when we look at Yoda here, what's happened is that this is going to be a preview of how the printer is going to go. And what we can do is that we can walk through the layers to see what they're going to look like. So with 0% infill and a wall thickness of 0.1 millimeters, we end up with sort of like the inside of the object looking like this. So it looks like a sort of a pretty hollow sort of model, the kind of thing that you typically get if you are, say, like, casting something out of bronze or something like that. So it's a real sort of like surface cast. But then the operational parameter here is wall thickness. So wall thickness is quite thin, right? 0.1 millimeters is extremely thin. So if you try printing this, you may actually end up with some regions that are almost like semi-transparent because they are so thin. So you probably want your wall thickness to be 1 millimeter at least. Probably, if you want something that's really stiff that maybe stands completely on its own with like no infill during the in the middle, you maybe want to say go with 2 millimeters, right? So if we change this to 2 millimeters, how different does it look? So if we go to 2 millimeters here, you can see that the center of the model is actually pretty thick, right? So compared to the rest of the model. So that's about 2 millimeters thick, and you've got a fair bit of detail that's there. However, it is pretty wasteful of material, and it does change the characteristics of the model. It's going to expand and cool a little bit differently, and you may get some warping. So you probably want to just leave this at, say, like 1 millimeter. And then let's instead futz with this infill density parameter, which is very, very, very useful and surprisingly great, especially for art prints. Most 3D prints that you have, you can get away with as little as like 15% infill. So what does that even look like? So if you go with 15% infill, this is what's going to happen. So when you've got 15% infill, what the slicer will do is that it will add material in the middle of the print to give it structure, right? So you can see here that it adds these lines in the middle, and it really does add a lot of strength without adding a lot of weight. So you can get away with something like 15% infill, and it will just add it to where it's needed. And in regions that are, say, denser, like around the ears and stuff, it will add more lines just to make sure that you don't have any regions that are completely unsupported. So most of the slicers do a pretty good job of figuring out where to add the right amount of infill. Now, there are going to be situations where what you want to do is that you want to make sure you want to have your object with 100% infill, right? So if you're printing out, say, like a crankshaft, you want to make sure that it's a pretty solid hunk of plastic. Even then, I think I would recommend not going past about 90% infill. The reason for that is that if you print out a solid hunk of plastic, as it cools, it will expand or contract in very odd kinds of ways. If you leave a little bit of airspace in there, then it will more likely cool in the shape that you intended it to be, right? So if we go with like 100% infill, it's going to show you what that looks like, right? So 100% infill looks like this. Go away. So 100% infill looks like this, right? So you can see this material is completely filled. And what it does is it just alternates directions as it goes, but it's extremely, extremely filled. And, you know, it wastes a lot of material. And like I said, it will lead to these weird sort of like expansion and contraction parameters. So if it was a model like this that was pretty small, I'd probably go with something like 80% infill. If I really absolutely needed to do that. But you can see here, there is actually this very sort of tiny honeycomb structure in the middle that allows for sort of air movement and air gaps. And it means that your object will cool in a much more natural way, and it won't get quite so wonky when you print it, and you're less likely to get sort of like warping problems as you go. So that's wall thickness and infill. The next two things that you need to know about are support and basically plate adhesion. So how to stick your model to the plate. So having a quick look at support here, there's really not much of a story to tell. What support will do is that it will add, if you have any parts of your object that are really hanging out into space, it will add material underneath it so that when it prints, it's supported, right? So what it's done here is that if we zoom in a little bit, you can see that, for example, like under his hands, it's generated a little tower so that his fingers have something to rest on when they get printed. Look at these two little wings that are on their back. They're not wings. They're there for his ears, because they're huge, right? So these little bits of support structure here are to make sure his ears get supported when they get printed. So that's the function of supports, right? And you can end up in situations where you end up with support material that gets printed on the model itself. So imagine like you've got a C-shaped hook on the model that's at the top of it. At the bottom of the C, you're going to get support material that gets printed in between the inner part of the C to make sure the top part of the C is generated. So most programs will have an option so that you can get supports, and you can only support the stuff that is hanging over the build plate rather than over the model itself. But most of the time, you probably do want to have just like leave the default and just have support printed everywhere. Another subtlety of this is that as far as supports go, you can still have very sharp angle things, but if the amount of material that's being added is small, then it doesn't put supports. So if you look at the bottom part of his head here, where his sort of like upper lip is jutting out, or even where his nose is jutting out, because it's such a small feature, no support structure is added, because it's kind of tiny, and it is even though it's quite sharp, it's relatively gradual, and it's within sort of like the limits of the material that's being put down. It's kind of close, right? So it's pretty smart in terms of trying to figure out where it's going to put down support material, and specifically where it's not going to put down support material. So that's that. The last thing that's worth sort of getting a handle on then is build plate adhesion. So the way that looks like is, I'm just going to put this down here. When you print out an object, especially if it's something large that has a lot of surface area on the plate, if it doesn't stick to the plate very well, what's going to happen is that as it cools, the edges of it are going to start peeling off the plate. And if that starts peeling off while you're printing, what it will do is that it will take those corners of the layers that it's underneath and actually cause the whole print to warp up at those corners. So you end up with this weird sort of like concave shape on the top of your print, and it's because the bottom layer has started warping already. And it causes, sometimes it causes the print to collide with the print head. It's not good news. So what you want to be able to do is that you really want to be able to stick your object to the plate very firmly while it's printing. I'm just going to run you through the build types, and I'm maybe just going to skip one because it's fairly simple. So one of them is just nothing at all. One of them is this thing called a skirt, and all that does is that it just it draws a line around your object. It's really not much good. But the first one where it starts getting interesting is that you generate this thing called a raft. And what the raft will do is that it will basically draw these concentric rings around the base of the object. And it will ensure that when you print, so they tend to be just a single layer thick, but that raft will stick really firmly to the build plate. And because it's this big sort of like flat, almost if you like leg that gets like an elephant leg that gets stuck to the bottom of the plate, the raft itself maybe will do, sorry, not the raft, the brim itself will maybe warp a little bit at the edges, but it will prevent, like, the center of it won't peel. So that will help it sort of stick really firmly to the plate, and it will stop the edges of the print going up. But I think probably if you can afford the time and if you can afford the material, and most people can afford the material, it's just a matter of time, because it does add a bit of time to the print. At least sort of like 10%, maybe as much as like 20% of the print time. You build this thing called a raft. And the raft I really like, and it's the thing that I would recommend for most people, especially when you're starting out. I almost never print without a raft. There's a very rare occasion where I don't use a raft now. And what the raft does is that it's a much larger piece of material that gets placed under the object, and there's a couple of things that are really clever about it. So when the raft gets put down, first of all, it's quite large. And the other thing that you to note about it is that if you look at the layers in the raft, it generates these crisscrossing layers that have air gaps in them itself. So what will happen is that it generates these air gaps so that the model actually gets printed on the raft rather than getting it printed on the build place itself, which means that there's a little bit of air circulation on the bottom of the object as well. Again, sort of like helps prevent warping. It means that it's really firmly stuck down, and it is quite nice, right? So when you take your model off, you have this fairly rigid base, and it's much easier. This rigid plate that you have, rather than say like a floppy rim, you can scrape off the build plate or bend it off the bendy plate if you've got a bendy plate, and it's fairly easy to get off the build plate. And then your object itself, you can just snap it straight off the raft, because it isn't extremely well stuck down, but it is still reasonably well stuck down. And it's a very nice mechanism for working with it, and you tend to get the least amount of warping. Like I said, the downside is that it already takes a very slow process, like 3D printing, and makes it even slower, but it does, much better guarantee the quality of your results. So it's something that I would highly recommend. It's pretty great. Okay, awesome. All right, let's talk a little bit about Tinkercad 2 then. So let me just go back to Tinkercad, and I'm going to talk a little bit about kit bashing. I think most of you folks are familiar with sort of this in one way or another. The idea being that you take existing models and you take them apart and you do something novel with them, right? So I was using Baby Yoda because he was convenient, but I'm just going to keep on using him as an example. But let's talk a little bit about sort of like, how you do kit bashing. And I think probably the first step in all of this is where you find your models. And I think Thingiverse is great for this. I'm on Thingiverse myself, so if I go to my profile here, a lot of the designs that I've made, it's not been a huge number that I've published. I've made a lot more things, but I haven't published more. I should really publish more. Like for example, like the microphone I'm using is on a 3D printed stand. But it's a good place for sort of like cataloging your builds and publish them and sharing them with people. But it's also a really great place for sort of searching for things, right? So so let me just repeat that again. So what you want to do is when you go to the Thingiverse page, you scroll down to Thing Files, and then you go and grab the STL or the OBJ that's associated with it. So, here's the beefy arms that I found, And then again, because I was just messing around with Baby Yoda, it was just in my head because I just watched this a couple of days ago. I went and found like the thing files associated with that, and I grabbed the model that's here, right? So I grabbed the Baby Yoda with the body. It's worth noting that when you are doing kit bashing in Tinkercad, there is a limit of 25 megabytes. So if the model that you import into it is larger than 25 megabytes, you probably want to run it through a tool like, say, MeshLab to get it down to a smaller size. So if you're not familiar with that, let me know, and I can run you through like a 3-step mesh decimation pipeline if you want to be able to sort of take your models and make them smaller so they're a bit more manageable. I think this one had like 300,000 triangles, which looks really cool, but pardon me, it's too much for a Tinkercad to handle. So you want to go with a slightly smaller version of that model. So in fact, that's what I did. So I went and made Baby Yoda a little bit smaller. So pardon me. So I've got him in here. I preloaded him because he does take a little while to load. Like, it takes a couple of minutes to load because he is 25 megabytes, and he's got to be loaded on to sort of like presumably Autodesk servers on the back end to get him ready for display. But I've got him right here, and what we're going to do is we are going to upgrade his arms. So I'm just going to run you through that process because it's pretty fun. So what you do is that you drag, because remember I mentioned last week that Tinkercad is all about constructive solid geometry. It's all about adding and removing things. So what we're going to do is we are going to remove his arms to start with. So I'm just going to move this up a little bit. What I'm going to do is that I'm going to try to avoid cutting into his body too much. But I'm just trying to be, I'm not being super neat here, just enough to sort of demonstrate the point. So we've got his arm here. I'm going to move this over a little bit, like so. So then I'm going to take that, I'm going to take my subtractive box, and I'm going to Control-C, Control-V, move it over to the other side, and let's see if I can pose it in a similar sort of position. Again, we don't have to be super accurate here when we're just sort of messing around, but I tried to get it sort of like roughly in the same pose on both, so I think I'm going to maybe move this up a little bit as well, just to sort of get in the same ballpark. Okay, so then what we do is you select all of them. So there's like, you can either shift individual click these, or you can use the rubber band tool to select the whole thing. And then what we do is we just go to our standard group operation, which you'll be familiar with by this point. So hit Control G, or just click the button. And what that's going to do is that's going to start calculating how to basically remove his arms, poor guy. So then what we're going to do is, while I'm waiting for that, I'm going to import my beefy arms. So here's my beefy arm, and it's worth checking the dimensions here. As imported, it's going to be 4 millimeters high, which is just way too small. So I'm going to change the scale of this to 500%. So it's a little bit more sort of a reasonable size, and I'm going to import the arms. So you can see Baby Yoda here is feeling very upset because he's missing his arms, but that's okay. He's going to feel awesome in just a moment. So we're just waiting for the arm to come in. I think is his arms. It's still tiny. So I'm going to take this here, and I'm going to take this arm, and I think it needs to be a little bit bigger. So I'm going to do that. Oh God, yeah, beefy Yoda. So let's see. I'm going to take that and shrink it. So I'm hitting Shift here to sort of make sure that the scaling is kind of uniform. And I'm just going to donate an arm just like this. I think, yeah, that's pretty good. But I think what it does is, I think it needs a little bit of rotating here. So I'm going to rotate it a little bit so I can, so it's not dragging along the ground quite so much, and then scale it a little bit. So this is where like using a real sculpting application is nice, right? So you can see here that the donation site is not that great. You can see that there's a gap here, and you'd use something like ZBrush or even Blender, or there's, in fact, if you want to use like a free tool, there's this thing called Mesh Mixer. Autodesk seem to make so many of these just like random tools. If you use Mesh Mixer, you can actually take an imported model and you can do some like really nice smoothing operations to sort of get things where they're supposed to be, right? So you can look at a join between two meshes and really sort of like smooth it over so it looks great. So here's Baby Yoda with one arm. So I'm going to take this and I'm going to hit Control-C, Control-V. There's a really nice mirror operation here. So I'm just going to use this to sort of flip the arm over. I'm going to take this over here, and then I'm also going to rotate this like so, and then yeah, that's awesome. Right, here we go. I just need to zoom out a little bit. Oh, come on. Okay, fine. Like so. Sorry, I know I'm fussing over the placement here, but it's got to be right. Move this over here, and then tweak this a bit, move it down until we're in the ballpark. That's roughly about right? So once we've done that, we've got Beefy Yoda. So again, you can just sort of like select all the objects, and if you hit combine, then what that's going to do is that's going to have a little bit of a think. And on the, basically what's happening is that this is not happening in your browser, or at least I don't think it is. I think this is all happening on the Autodesk side. It's just having a think about how it's going to combine all this geometry, and it's doing all the geometry processing operations. But basically, once that's sort of cooked up, that's going to be ready to print. So when you export this object, you can then get it straight into your slicing application, and that's going to be there, like, ready for you to sort of like print and like sand and paint if that's what you really want to get into. It's worth noting, sort of like, whoever designed this model really did think about how it's going to print, right? So when you're printing with a typical FDM printer, the thing that you want to be able to do is that you want to be able to minimize the amount of support that gets generated, because anywhere that needs support is going to be an underside of the model, right? And the undersides of the model are going to lack a lot of detail. They're going to look rough, right? Just like you saw with these pieces that I was showing you, right? Anywhere that you're going to have the underside, anywhere that you're going to have facing down on the build plate is going to look not so great. So if you actually look at the underside of this model, so minus the beefy arms, you can see the area around these ears is, these leading edges on the bottom are pretty thin. Where his hands were sticking out, they were pretty thin. They were still like very, very, very close to his body. So, somebody really thought about how am I going to make this model so it looks good when it prints, right? Even here, like, with the collar doesn't come out too much. So, it's designed in such a way that it will print with a minimum amount of supports. And I think when you're working on your own designs for models that you want that are a little bit art-based, you really want to think about how are you going to arrange things so that the minimum amount of support material is there, the minimum amount that is going to be facing down on the plate. And when you design your model, you don't necessarily have to have it the right way up, right? So, for example, like let's just say you're designing a really simple thing. You're designing a table, right? So you're designing a table, so it's got a flat top and it's got 4 legs that are sticking out. So the thing that a lot of people will do the first time is that when they print it, they'll print it so that the legs are facing down, and then you got the top of the table here, and you print all this support material on the bottom of it. And the bottom of the table is not going to look so great when you take all that support material off. So what you can do instead is that you can take the whole table and just flip it upside down. So you got the flat end of it down at the bottom, and you got these legs that are going to be sticking straight up out of it. There's no support material required at all. And that's going to come out as a nice, sharp print, right? So they're also different. Like, when you have your art object, there's nothing that is dictating that things have to be up a certain way, things have to be oriented in a certain way. You can just get it wherever you like, so it's going to look best on the print bed. So yeah, that's that. It's not too bad. So I think for the assignment then, what I'm going to do is I'm going to ask you to just do some kit bashing. So find something cool or interesting on Tinkercad, and or wherever, right? So find your OBJs, find your STLs, find your 3D models, get them imported into Tinkercad, and just try sticking some things together. Make it as nuts as you like. I will email out a link with the beefy arms if what you want to do is just add beefy arms to things. I can't help doing that. It's a lot of fun. But do whatever you like, and I think I'll take a couple of those and I'll try printing them out, and then we'll talk about how it came out and what worked and what didn't. Again, I really like that idea of doing that. It's a nice way of sort of like really interactively having a go at like understanding some of the subtleties of the printing. I think it's going to be pretty fun. Okay, any questions, folks? Looking good. Awesome.
Actually, I have a question.
Yeah, please
Both.
go for it.
You didn't talk too much about the actual like support struts, how they get generated. Like you talked a lot about infilling, for instance, and but does it pretty much work out of the box usually? Like the
yes.
Yeah.
Yeah, I almost. There's been a couple of very rare occasions where I've wanted to put in the supports myself, but 99.9% of the time, just let the software figure out where you're gonna put the supports. There are things where what you can do in some of the applications, I believe you can do this in Cura as well. You can actually paint on the object, and you could say, "I definitely don't want struts here." Um, and you can actually tell it. You can actually tell it it's like, don't worry about the struts. One of the other things that you can do is you can also change the angle as well. So what will happen is that in the case where I had those three triangle objects that I printed out. In fact, let me show you something. Let me just bring this up. Sorry, just bear with me a moment. I've just got to find my model. I'm not sure. Actually, I have it. No, never mind. It's not going to work. When you have your objects that get printed out, let me just show you this again. I'm just going to bring these three up. Basically, the steeper it is, the more likely it is that it's going to put supports there. So let me just get the overhead view again. So, for example, for these three objects that I printed out, this one, no supports. This one, no supports, but this one did, right? And what you can do is that you can change the angle of that. So that's one of the parameters that you can change. So you could say, you could actually have it lean out much, much, much further, and then it will change when it's going to put supports there. And that's where, if you're confident that like your object is small enough, or if the tolerances aren't, if you don't care too much about it and you don't want to have the extra time of printing out those supports, you can say like, don't worry about it. I'm just going to go with what it gives me. So that's definitely it's an advanced parameter, but most of the slicing applications will give you access to something like that, if that makes sense.
Okay. And then for something like this, do you still print a big base as well, like you mentioned?
Actually with these, it was kind of funny. Let me show you the print base here. So with these ones, let me just go back to the overhead camera here. With this one here, you can see like I wish I'd kept, actually, I just chucked them out. I wish I'd kept them. I printed rafts for all of these, and for this one here, because I had the supports, you can see the raft is pretty big. But when I told it not to print the raft, it was only about that big. So I had this little square of material that was on the bottom there, and that was all that was needed to adhere it to the plate. Right? So, I had another version of this that I printed out with, in fact, this is the one I printed out with just the raft. And it didn't come out too badly, right? And it didn't tip over. And it's worth noting that, like, all of these have 10% infill. They're mostly empty. So they're not super, super, super heavy. So if you've got like a chunk of the model which is sticking to the plate, it will stick there. And the same with this guy as well, right? So when I printed this one out, the raft wasn't underneath these fingers at all. There was nothing that was underneath these fingers. It was only on the bottom part. It was only on this sort of leading edge of the plate, and that was more than enough to sort of stick it to the print bed to print. So you can get away with like a relatively small amount of the model is sticking to the plate, because most of the time the models are really, really light. Cool. Awesome. All right.
So
Any other questions, folks? Yeah, please go for it.
yeah, I didn't really work on the assignment past what I was doing live the last time, but
That's all right.
no, but I actually learned a lot. I had played with Tinkercad before, never
Right.
realizing that you could group things. So I was doing Boolean operations, but leaving everything live. So just the Control G or Apple G in my case just made me work 100 times faster. And so I did. One of my daughters is fascinated by ladybugs, and I managed to do one like in 20 minutes. Right? It was
I
took
love it.
nothing.
Yeah.
And I printed it for her, and then she painted it, and she was very, very, very excited. So
Oh, that's
already I
exciting.
learned something last time. I don't know if
Oh,
I can show
cool.
you, but because unfortunately, I now have the learning account on Tinkercad in my own, so
That's
I don't
fine.
think I can share it with you. But
It's cool. No, don't worry about it. It's cool. I'm
sure.
I'm excited to hear it. Did you end up? I'm just curious. Did you end up building a library of parts? So did you build one leg and then you just replicated that out to
Um,
the rest?
does it have any legs? Again, it's
Got it.
very trivial, right? So
Got it.
it's a modify an ovalloid. I cut the bottom. Another ovalloid. I made the head. Made holes to mark the spots that she could paint. And then a line in the middle. And that line took me a while to just scale a copy, make it smaller, cut only that part, remove it from two sides. So it was a little bit involved, but it only took me like 20 minutes. And
fantastic.
If I find a way to paste it in the account that is shared, that is part of the lesson,
I love it. You know, I still use Tinkercad very, very regularly. It's actually an excellent, I mean, for those of you familiar with sort of like the 3D terminology, it's really good for blocking, right? So when I'm doing my 3D design, what I'll do is that, because it's so much, when I'm just like iterating on an idea and I need something more than pen and paper, I will use Tinkercad to initially lay out the blocks and the shapes, and sometimes I'll actually print those just blocky bits, right? But the thing is that you can do it so fast, like much more so than like a CAD application. And then what I'll do is that once I have that, I'll use that as a reference. I won't import it directly into a high-powered CAD tool like Fusion 360. Most of the time, I occasionally do. But then, I've got those, and I use those measurements then to come up with something more formal. And then I'll go to like to Tinkercad. Then I'll go to like Fusion 360 to do a better design. So I think I know it seems like a bit of a dinky tool at times, but it is worth knowing because it's a useful tool to have in your toolbox when it comes to sort of like iterating on the 3D design. So it's definitely worth learning. Yeah, for sure. I'm glad you're enjoying it. That's cool.